So this is just another example of a catalytic mechanism, and this specifically is for the enzyme chymotrypsin. Chymotrypsin is a protease and it falls into the class of serine proteases. Now, this has a mechanism that's fairly complicated, but we've broken it down into several kind of simple steps. And what I want to do is highlight what some of those important steps are. Now, the first thing that I'd like to do is highlight what is the substrate and what is the enzyme. Okay, so I'm literally highlighting now in yellow my substrate. I'm going to only do that for the first two cells. But what I also want to do is I want to be able to identify where is the bond that I'm actually breaking. Now, like I said, this is a protease, so it is a protease, in which case it's going to be cleaving a peptide bond, and the bond it's going to be cleaving is right there. Similarly, right here in those first two cells. So it is breaking a polypeptide down into individual pieces. Now, the reason that this is a serine protease is because this enzyme, chymotrypsin, has a serine in the active site. Okay, now that's the first thing that I'd like to point out. So the active site, so this kind of bottom part here, that is our enzyme. Now, what we've done is we've reduced it down to basically the amino acids that are in the active site of that enzyme. So the serine residue here is one of the hallmarks of a serine protease. Every serine protease has a serine within the active site. This also has a histidine and an aspartic acid. Okay, now one of the keys to catalytic mechanism is to identify what are the individual amino acids and what are they actually doing. Okay, so here we've got a serine residue, and what is that serine residue doing? So from step 1 to step 2, or from cell 1 to cell 2, what's happening here? Well, one of the things that's happening, I'm going to erase some of my markings there. One of the things that is happening is we're forming a linkage between our amino acid, our serine residue, and our peptide. Okay, so what type of linkage is that forming? Well, this is a carbon right here. It's a carbonyl carbon, and this is going to serve as an electrophile. Therefore, our nucleophile is our enzyme, or is this serine residue, nuke. Okay, so by forming this bond between an electrophile and nucleophile, well, this is an example, and by forming a bond between a substrate and the enzyme, this is an example of covalent catalysis. Now, what's going to happen whenever the nucleophilic serine residue forms that bond, that covalent bond with our electrophile here, is it's going to be able to give up the hydrogen that was previously on that hydroxyl group. Well, lo and behold, there's an adjacent histidine within that active site that's there to pick that up, because this histidine residue is deprotonated, and since it's deprotonated, we know that we have this lone pair of electrons. This lone pair of electrons can pick that up. So effectively, this bond right here goes up there. Okay, so now we've got this bond between our enzyme and our peptide. Okay, now what's going to happen whenever that goes on, we're going to get a negative charge on this oxygen. Whenever we get that negative charge up there, what that is going to give way to is it's going to give the nitrogen here the ability to be protonated. And whenever that nitrogen gets protonated and takes on a second hydrogen, well, then that basically is destabilizing our peptide bond there. And if you look between steps 2, 3, and 4, what you see is that we have our protonated N-termini, our peptide bond is still intact, and then in cell number 4, what's happened to this part of our polypeptide? It's gone. Okay, so we have no longer we no longer have that peptide bond there. So basically, by step 4, we've done everything that we need to do. But the important and wonderful thing about any sort of catalytic mechanism is we have to basically return every single one of those residues to their starting state. Okay, so sorry, that hydrogen there that protonated our N-termini, well, that is going to come from our histidine here. So that histidine that picked up the hydrogen from our serine, well, that's going to go on there. So now we've got a linkage, a covalent bond between our serine and our substrate. We've got this deprotonated nitrogen. Have I said anything about the aspartic acid that is right here? No, because that aspartic acid isn't actually doing anything. Okay, so now what's going to happen if we look over in cell number 5? Well, we still have our covalent linkage between our serine and our peptide, but we also have water in that environment. Our carbonyl carbon is going to pick up an OH from that hydrogen. That OH is also going to act, or sorry, that water is going to act as an acid because our histidine residue that's acting as a base is going to pick up that hydrogen. By picking up that hydrogen, now all of a sudden we have a protonated histidine residue, histidine number 57. We have a carbon that has a single bonded oxygen with a negative charge, a single bonded OH group, and then we still have that link with our serine residue. But now what we can do is use the electrons from that serine to substrate bond to pick up this hydrogen, return these electrons to our nitrogen. Now we've returned to our lone pair of electrons on our nitrogen, and we have our serine to its original starting state. Now what's interesting about this is our aspartic acid basically did nothing. And not to say that it was lazy or anything like that, I don't want to ridicule the amino acid, but essentially all that it did was it played a structural role. So it was there not to be involved in any sort of pushing of electrons or anything, but it was there to take a kind of structural position and basically kind of maintain civility for all of the amino acids in there. Okay, now these next few slides, basically the exact same information, but it's displayed in a slightly different manner. The steps are a little bit more deliberately laid out. I just want to write out this is step 1, 2, and then from 2 we go on to 3, 4. Then once we're at 4, we've got 5, 6 where our water comes in, and then 7 and 8. So it kind of goes in a clockwise fashion. So rather than it being 7 steps as I worked through it, this is displayed over the course of 8 steps. Now, one important thing that we've talked about with respect to enzymes is the transition state. Now, quite commonly,